Good morning, or afternoon, or whatever the time may be. Had some requests for doing some review material, so especially on rotational systems. Thought perhaps we'd start off with this one. We got an inertia, couple of inertias up there, and a mass, linear spring, torsional spring, and an extensible cable, so on and so forth. So let me go ahead and start off with that problem. This is off the test 2, I don't know, maybe it was actually test 3 of 2016, I'm not sure which. But it'll be on your test 2. Not this specific problem, but a problem similar to it. So anyways, what we've got, drawing it out, is, like I said, an inertia here. That's J1. And we've got another inertia over here connected to it, which is J2. And this has some radius R2. This will have some radius R1. We've got an inextensible cable pulling down, or to which we've applied a force. F sub A, we're going to neglect gravity in the situation. Now over here, we've also got another inextensible cable attached to a mass, like this. We'll call that M. And there's a spring down here, a linear spring. We'll call that K2. Let's go ahead and measure the displacement of the mass M upward as X. Let's measure the rotation of J1 clockwise as theta 1. And it truly makes things a little bit easier if you make these equal and opposite. Well, not equal and opposite. Definitely not equal and opposite, but you make the different angular rotations opposite on those. Now the supposition is that this one is kind of held in place by a bearing, okay, on this side and on the other side. And then this system is actually connected to a wall by a shaft, which I'm going to represent with one of my quirky little devices like this. So our connecting arm, connecting rod, whatever you want to call it, crank arm I guess is what I should call it, like so. And wouldn't hurt to have another color in there just to show the spring. Okay, and so in that sense, that the stretch in that spring then will be represented by theta rotating in the theta 1 direction. Not terribly great projection, is it? These are in this plane, that one's in that plane. I think we can live with that. I can live with it anyways. I hope you can too. So, neglect gravity, let's see. First job, draw the free body diagram for each inertia and the mass. Alright, so that's not too hard to do. There are a couple of things that you need to keep in mind as you do that. I guess I'll do it over on this board, but we can always look from a projection, or I don't know what you call this, orthogonal view. There will be some tension in that cable. That's going to be applied to the mass. And then also, as I've suggested in class, make sure that you have the tension and the radius applied right there. Let's see, that's the interface there. The mass is positive upward, and therefore an MV dot is going to be downward. There will be some displacement, some displacement of the mass, positive up, meaning that there will be a force, FK2. I'm going to assume that's acting in tension, and it's pretty obvious to see that stretching out K2 just is the direct translation X going up, and so this should be K2 times X. I did neglect to say this is actually K1 is the torsional spring that we got up above. So I've got that force, we've neglecting gravity, we've got the spring force, the tension of the cable, and the inertial force acting on the mass. And that's it. Up here, we've got a force acting at a radius on this inertia J1. In addition, we have got an inertial torque acting in opposition to theta 1, and so we should expect a J1 omega 1 dot to act in a counterclockwise direction, since theta 1 is positive clockwise. Back here, if that spring is in tension, yes, we're rotating it as a negative theta 1. In addition, though, the other thing that we need to visualize here is that the force, the torque due to it will be in a clockwise direction. And so what we're going to get out of this is a spring torque like this, tau K1, which is equal to K1 theta 1, and that should have been a negative K1 theta 1 up there. The other torque that we have acting on that inertia, we've got the tension here, we got the inertial torque, we've got that spring torque. We also have a gear torque, if you will. That's what I've been calling those, a gear force acting at this point. Is it going up or is it going down? Doesn't really matter. I guess since this one's pulling down, well, that's not even a conjecture on that one. Let's just make that gear force acting down like this, F sub G. And once again, I don't think it's a bad idea to put your radius in right there to sort of remind yourself that it's acting in a radius R1. Now, as soon as you draw that F sub G, you should also be drawing another F sub G, equal and opposite in sign, acting about J2. And also, since we got that R1, we better make sure that we see an R2 over here. That's for J2. Now, what else is acting on J2? We've got an applied force, which will create a torque acting downward on that. So we've got this force here, F sub A, capital F, sure. And once again, I have an R2 like that. Finally, the inertial torque acting about J2. Theta 2 is positive in this direction, in a counterclockwise direction, so J2 omega 2 dot should be acting in a clockwise direction. It should act to oppose that positive sense of motion. So we have a J2 omega 2 dot right there. That's it. That's the free body diagram. That's the first question on this test assignment, was how to draw how to draw the free body diagram. The next was developing the basic equations of motion for each of the three masses. Do not solve for the spring forces yet. Leave answers in terms of Fk2, tau K1, F sub A, Fgt, etc. Well, I guess I kind of cheated a little bit. I already got my K2x here, which is equal to Fk2, and I've got my tau K1, which, well, yeah, I already said tau K1 equals that. So let's skip the equations of motion and go ahead and put those in. Basic equations of motion. I guess I'll start down here on that mass. Some of the forces on the mass, I'm going to make them positive downwards because mv dot's positive downward. You don't have to do that. You can make them positive upwards. It doesn't really matter. I just happen to be in the habit of making it so that my inertial force or torque tends to be positive. So I would have then an mv dot acting downwards, a minus t, and a plus Fk2. So let's go plus Fk2 minus t is equal to 0. And part C there says, what's the stretch in spring K1? Oops, let's see, that's part D, must be the force in the translational spring at K2. That's this K2x. So I'm going to go ahead and short circuit the process here. Just say mv dot plus K2x minus t is equal to 0. And we'll leave it like that for now. Moving on to our next inertia. I'm going to go ahead and sum the inertial torques positive in a counterclockwise direction. Again, my reasoning is that J1 omega 1 dot is positive in the counterclockwise direction. It's perfectly legitimate to sum them positive in the other direction. Maybe I'll do that for J2 just to demonstrate that. So let's see, some of the torques, J1, and I'll make them positive counterclockwise. And so I have a J1 omega 1 dot, let's see, plus T times R1 minus FGR1 and minus tau K1 is all equal to 0, or J1 omega 1 dot. I'm going to leave these two alone for now. They're internal forces that I'm going to need to eliminate, T and Fg. I'm going to go ahead and say negative tau K1 is going to be negative of a negative K1 theta 1, so that makes it a positive K1 theta 1. So now we have plus T1 minus, and I lost my R1 there, plus T times R1 minus Fg R1 is equal to 0. And we can leave it in that form again for now. Finally, the inertial, the equation of motion, the basic equation of motion for that system, just because to show you that I can go in the other direction. If J2 omega 2 dot is positive in a clockwise direction, we'll go ahead and sum the torques positive in the counterclockwise direction again, just because. So, sum of the torques, J2, positive counterclockwise, means that I have a negative J2 omega 2 dot, right? I'm going to get negative on that. I have a negative FGR2, and I have a negative F sub A R2 is equal to 0. But you know what? If I sum them positive in the clockwise direction, I would have had J2 omega 2 dot plus FG R2 plus F sub A R2 is equal to 0. Those are really the same equation, aren't they? The top one, you multiply both sides by -1, you get the bottom equation. My point that I'm trying to make to you, and I hope that you're following this carefully, some people already understand it, other people are just kind of blindly, okay, step. Check it out. It doesn't matter. Since you're summing the torques and setting them equal to 0, you can make them positive in one direction, positive in the other. It's okay to take either approach. Generally, I happen to like dealing with positive numbers. Let's go ahead and worry about what to do next, I suppose. So, like I said, I've already done now I've done steps A and B, the free body diagrams for each inertia and for the mass. I've got the basic equations of motion for each of the masses, mass inertial elements, I should say. I got the stretching spring K1, I've got the force and translational spring K2, and so now the subtlety comes into play. Solve for the cable tension in terms of the motion of the mass M. I was trying to leave breadcrumbs through the forest, is the expression that I like to use. Trying to say, hey, look, ultimately my answer is going to be in terms of theta 1 and omega 1. That's the final space form that I asked for on this homework assignment. Don't know how clear it is at this point, but I'll hold it up anyways, and maybe you can zoom in, maybe not. And so let me talk about that for a second, and then I'll go ahead and finish the problem. Well, all right, let me put it this way. The final answer should be in this form. Theta 1 dot omega 1 dot is equal to some function, and it's going to be a square matrix. If I got two elements here, this better be 2 by 2. Theta 1 omega 1 plus some two-element matrix times F sub A. And I asked that in the assignment. That's what I actually say, the final answer, what I wanted in. I want you also to understand that this is one approach. I could have also asked for my answer in terms of x dot v dot is equal to some, again, square matrix 2 by 2 times x and v plus something times the input. That's a legitimate form as well. Finally, I can also replace these the one with a 2 right there and there and there and there. So I could have theta 2 dot omega 2 dot is equal to some function of theta 2 omega 2 plus something times FA. I can't mix and match. Whatever this vector is, this has to be the derivative of it. Whatever that vector is, that's the derivative of it. And in all cases, my input is over there. That's the applied force. In some cases, it might be an applied torque. So there are 3 possible combinations. And if you want to get into the mathematics of it, there are even more combinations. But let's not do that. Not even going to say we did. But I'm bummed. All right, enough of that. So, the point is, let's stick with what we're asked to do in this assignment. Well, when I wrote it up, what I asked the students to do, I guess, in the summer of 2016. There is no FG in here. These are constant coefficients. FG will vary. It's an internal force. It's going to go, sometimes it's 0, sometimes it'll be positive, sometimes it'll be negative. We could solve for it. We could do that as an expression of the other elements in the system, but I don't think that's a great idea. Well, actually, we can solve for it. I'll show you how in a minute here. It's not going to be a single value, though. It's not going to be 5 newtons or something like that. It would be a function of the states, and the input, actually, is what it would really be. But the point is that I'm trying to make, there is no FG explicitly defined or shown in here. There is no t explicitly shown in here. So in these equations of motion, we've got a t right here, we've got an fg there, we've got an fg there. We need to get rid of those. Further, we don't have, in the form that I asked you to report the answer in terms of theta 1 dot and omega 1 dot, in terms of theta 1, omega 1, and fa, because that's really what I'm saying is, give me these two derivatives in terms of the inputs, theta 1, or the states, theta 1, omega 1, and fa, and then these are just the constant coefficients you're solving for. I don't have an omega 2 dot in there. There should not be an omega 2 dot or a theta 2 in your answer. I don't have a v dot. I don't have an x. There should be no v dot or no x and no v for that matter in your final answer. So we're going to have to get rid of those. So what I'm suggesting we do is we recognize, I've got to eliminate, for example, t. Well, let's get rid of it then. Let me erase some of that board and go backwards on this. Here. I can solve that expression for t. T is actually equal to mv dot plus k2 times x. Now what's interesting about it, another way of looking at it is saying, hey look, I can express the acceleration of that mass in terms of this, well, I mean, you could solve for v dot is equal to negative k2 x over m plus t over m. All right, so the acceleration is equal to the tension in that cable and the position of the mass at that instant time, because that position defines how much the spring force is. So that's how we could solve out for the motion of that mass. We might want to. It's a very long way to do that. But I'm trying to demonstrate to you the mass can to some extent be taken in isolation if you only knew what t was. Well, we don't know what t is. There's a lot more to it than that, I suppose. Let me just stop there before I dig myself in too deep. So let's go ahead and solve out for that. T is equal to mv dot plus k2 times x. Well, we'll use that. What do we do with it? Well, we're going to plug it into this expression in a minute here. The next breadcrumb that I asked for was solve for the gear force in terms of the motion of the inertia J2. Solve for the gear force. So I take a look at that over here. I can actually say, okay, Fg is equal to, I'm going to leave that there, I'm going to move everything else over to the right side and divide by R2. So that's going to be minus F sub A over R2 minus J2 omega 2 dot also over R2. Oh yeah, that's R2 over R2, so they cancel out. The FAR2 divided by R2. All right, so we now have two expressions. I've got an expression for the tension of the cable. I've got an expression for the gear force in terms of the applied force and that acceleration of that little J2 that we have sitting over there. We can put those two expressions into this expression. All right, we'll have J1 omega 1 dot, okay, plus, all right, we have T times R1, well, let's see, I'm going to go ahead and plus K1 theta 1, like that. We got that expression term, that term, plus T times R1, so plus this expression times R1, plus MV dot R1, plus K2X R1, all right, minus FGR1, so it's minus a minus FA and a minus J2 omega 2 dot over R2. And this is where a lot of people tend to make the mistake on the test. They'll go ahead and get excited about saying, okay, plus FA, and then they jump into plus J2 omega 2 dot over R2, and they forget, I often forget, the R1. So there's an FA R1 plus J2 omega 2 dot over R2 times R1. And all this is going to be equal to 0. What you see here is that we've got a J omega dot, some kind of an acceleration term here. We've got another acceleration term here, and we have a third acceleration term over here. We also have got this is a spring torque. We've got an applied torque, and we have another spring torque like that, if you will. How do we substitute these, or what do we do to clear things up here? Well, we can go back to our original diagram over here and take a look and say, okay, let's take a look at the easy one first. How do I relate x, K2x? Okay, how do I get rid of x? And since that's a displacement, I'd like to get it in terms of displacement up here. We see that there's an inextensible cable here. We can actually say that x is equal to r1 theta 1. Because that relationship exists, we also could say that v is equal to r1 omega 1, and also v1 dot, v dot, my mistake, is equal to r1 omega 1 dot. This is the second derivative of that expression. So we can actually replace over here this mv dot. This is going to go to, what did I just say, an r1 omega 1 dot. And a lot of people sometimes forget that make it an r1 squared type expression right there. The x is going to go up to r1 theta 1. Okay, and don't forget, again, that extra r1 right there. Now, what else are we going to do? The only other expression, because we're kind of clearing things up a little bit. We've got an omega 1 dot here, and omega 1 dot there. We got a theta 1 and a theta 1. That's good. We have the input right there. That's good. Omega 2 dot. Well, how do we get omega 2 dot? Well, we recognize that in here there's some displacement. Okay, I'm going to call that x sub g for the displacement at that gear tooth, if you will. And what I know is that x sub g is equal to, check it out, it's r1 theta 1, like that, and it's r2 theta 2. So because of that, I have that theta 2 then is equal to r1 theta 1 over r2, which tells me now that omega 2 dot, being the second derivative of theta 2, is equal to r1 over r2 omega 1 dot. So now I go over here, and in place of my omega 2 dot, I'm going to go ahead and put in an r1 over r2 omega 1 dot. Now, again, r1, r2, we're going to multiply that by another r1 over r2. So it actually tends to have a squared type behavior. Not always, but often. So don't forget, you have to have a lot of attention to detail. Be very careful with how you do those. Putting that all together, let's go ahead and figure this out. Where should I put all this junk? I have a J1 omega 1 dot, that's my first term, and let's go ahead and put in the other omega 1 dot terms, and let's not do this as an omega 1 dot, right? I have a J1, that's going to be times omega 1 dot. I have an M R1 squared. Alright, so I've got this term, I've got that term, and then I've got a J2 R1 squared over R2 squared. All that's times omega 1 dot. Let's do my theta 1 term expression next. I have a theta 1 expression, whatever you want to call it. K1 theta 1 plus K2 R1 squared theta 1. So now I have plus K1 plus K2 R1 squared theta 1. And all this is going to be equal to a minus f sub a, and I'm going to put the r1 in front, minus r1 f sub a. Alright, so I switch sides with that fa r1. What's interesting is, if we pull on this with a negative fa, we pull down, that's going to rotate this one in a clockwise direction, that goes in a counterclockwise direction, so yes, it should lead to a negative acceleration of J1, and we see that here when we solve out for that omega 1 dot. So we can now put this in state space form. Trying to decide where the right place to delete all this is. I guess that's probably enough for now. I can delete this stuff. Putting it in state space form. 0, 1. And let's see, our theta 1 term is going to be k1 plus k2 r1 squared. Negative all over j1 plus m r1 squared plus j2 r1 squared over r2 squared. Yep, got that right. Okay. That's very interesting. I'm just trying to speculate here. As R1 is larger than R2, okay, the larger we make R1, the more that amplifies the effect of J2, R1 relative to R2. So as we get this bigger and bigger, then the influence of J2 doesn't grow relative to J1 because that would also get to be bigger and bigger. But the influence there, and that's because it's actually spinning faster and faster the larger we make R1 relative to R2. If we shrink R2, for example, let's leave R1 fixed, and we make R2 really, really big, okay, then we actually get less inertia out of J2 than we would otherwise. Or if we make R2 really, really small, then the influence of J2 goes up. So, let's see. Enough of that. 0, 0, let's see. Once again, you got theta 1 dot there and omega 1 dot there, you better have theta 1 and omega 1 here, plus 0, and it's going to be negative R1 over J1 plus MR1 squared plus J2 R1 squared over R2 squared, all that times F sub A. Sorry about the squiggling in there, but if you have to, rewind and listen to what I had to say about it. As far as it's a negative R1 in the numerator, the denominator is J1 plus MR1 squared plus J2 R1 squared over R2 squared. Alrighty then, as they say, that's the answer then to this rotational problem. So, hope that helps, and I'm going to stop this recording and move on with another one.